Hello, good morning, good evening, good afternoon, everybody, wherever it might be. Schönen guten Abend, everyone. It is my great pleasure to welcome my friend and colleague Ralf MEYER aus Göttingen. And today he will tell us about his joint work with my nephew, Gilles de Castro, who is in Florianopolis. And it will be about graph morphisms as groupoid actors. Meine Damen und Herren, Ralf MEYER, it's all yours. Take it away.
Thanks for the introduction, Piotr. And so I'm reporting on a joint work with Gilles de Castro, as he mentioned, which I did while visiting Florianopolis, which was supported by this nice grant that Piotr organized. So thanks for that. And so the main point maybe is if you want to have some take-home message. So we all know that graph C-star algebras also are groupoid C-star algebras. And these underlying groupoids also have a nice universal property. And using this universal property, you can, well, define some kind of morphisms between graph C-star algebras. And it turns out that the morphisms you get generalize something that was previously studied by Gilles de Castro and Francesco D'Andrea and Piotr Hayat, and I think it was only the three. So I want to tell you about this universal property and how you can understand then the graph groupoid as being something a bit like the graph algebra defined by some universal property. So the question might be, oops. Okay, so we want to have a universal property for this boundary path groupoid. So that's the standard groupoid model for a graph C-star algebra that people always use since, well, I suppose the first papers on graph C-star algebras, where Jean Reynaud probably was the person who insisted on using groupoid technology to study graph C-star algebras. Of course, to talk about universal properties, you would need some category of groupoids. So what is the right category of groupoids? And maybe before I talk about this category of groupoids, I might also give you the final answer. Or, well, maybe I should first give a name to this category and mention the difficulty. So probably you have heard that groupoids are small categories in which all arrows are invertible. And then if they are categories, of course, you know that functors are an obvious way to turn them, to make a category out of categories. However, functors do not work mainly because the groupoid C-star algebra is not functorial for them. So if you want to have some category of groupoids that has something to do with groupoid C-star algebras, and we want that certainly, you need something else as maps between groupoids. A good notion for this was already introduced a long time ago by Bunici and Stachura. So I don't know why their preprint never got published. Maybe Piotr knows more about it, maybe he doesn't, but this is probably for discussion after the talk. They named these morphisms after Zakrzewski. But I prefer a different name. So I've also called them different names in different papers. Nowadays, I like to call them actors. This sounds a bit like functors, and it highlights that they have something to do with actions. So I call them okay. So there is different ways to describe these morphisms. The most workable definition might be, Piotr, we can't hear you.
Can you hear me?
Yes, I can hear you now.
Okay, because I
So if you want to say something, we can hear you.
yeah, fine.
So what is an actor? So this is a quick definition what an actor is. So you take two étale groupoids G and H, and then you want an action of one groupoid G on the arrow space of the other groupoid, a left action, let's say, and this should commute with the right translation action of the groupoid H on itself. Nowadays, I have also talked about groupoid correspondences. This is another way of defining something like a category of groupoids. This will also become relevant in a moment. So maybe I also define this just to have some more context. And to explain why these actors might be the right thing to look at. So for a certain reason, I like to draw these arrows from right to left. The reason is that in groupoids, you have these source and range maps, and you want products to be defined if the source and range maps match appropriately. And this works better if I draw arrows like this for some reason. So such a groupoid correspondence is a space X By the way, if anybody wants me to tell you about definition of groupoid actions, these kinds of things, then ask me, please. I would hope that you can work with them without me explaining them, but if you need them, I can, of course, give you more definitions about these basics. So a groupoid correspondence between the two groupoids G and H mean that you have another space X, and you have actions of G on the left and H on the right, which commute. And you want that the anchor map for the right action, which I call S like source map. This is a map from X to H0. This is supposed to be a local homeomorphism. And you also want that the right action, well, I suppose that's a different symbol here. So the right action, maybe I write this symbol. So this means the H action on X. And this should be free and proper. So a nice kind of groupoid action. Probably you have seen these things in connection with groups more often than with groupoids, and you can generalize actions of groups to groupoids, and proper actions also make sense for groupoids. If you want to know more about this, then please ask. If we now compare the definition of an actor into groupoid correspondence, you see that an actor is a special groupoid correspondence where the space X is just the arrow space H.
Sorry, Ralph, I have a naive question.
Yes.
When you have a free and proper action of a group on a space, then quotients are really nice, like Hausdorff. Do you have a similar effect for groupoid?
The orbit space is Hausdorff. Yes, that's actually. So there's two conditions. One would be like for principal bundles. So there is this particular map, kind of composition. So XH goes to XH. This map is supposed to be a homeomorphism onto a subspace. Yeah, not open. It happens to be closed, but that's not part of this definition. So it's these two conditions combined. There's supposed to be this homeomorphism from X times H to a subspace of X times X. And the orbit space has to be Hausdorff, and then you call the action free and proper. Maybe another technical remark at this point. My groupoids are all locally compact, but they don't have to be Hausdorff, just Hausdorff object space. That's always required. That's what you need to define the C-star algebra of an Étale groupoid. And if you look at my main example, actors, so the space X could be the arrow space of one of these groupoids. And since I allow non-Hausdorff groupoids, the space X also has to be non-Hausdorff. And so I need to worry that all my theory of free and proper action works for these non-Hausdorff groupoids acting on non-Hausdorff spaces. And it all does. And there's a paper by Celso Antunes. Maybe I should also give the reference. Antunes, Co, and me. And I think we only have one paper by the three of us. Kind of, this works even for non-Hausdorff groupoids. When I say this works, I mean, so there's a lot of theory to be developed and it all works. And for the Hausdorff groupoid, this is probably kind of well known to the experts. In the non-Hausdorff case, it's also known, but maybe not so much and not so much documented. So that's a place where you could read about this. And now I can finish what I was starting before, Peter's question. So an actor is just a groupoid correspondence with X equal H as a right H space. So that's how these things are linked. And when I say this works, in particular, an important thing is that you can define something like C star X. This will be the C-star correspondence where the two groupoids act on the left and right as usual. So also here, I'd like to draw arrows from right to left for certain reasons. So there's a way of taking functions on X and putting on a scalar product to make this into a Hilbert module over C star of H. And then C star of G is acting on the left, making this into a correspondence. So a Hilbert module over one algebra with a left action by adjointables of the other, which is also non-degenerate. And this is also compatible with a suitable composition of groupoid correspondences and a tensor product for C-star correspondences. Okay, so I've now defined groupoid correspondences and groupoid actors. And if you think about this construction of C star X for a groupoid actor, you see that C star X is just C star H again. So for a groupoid actor, C star X is just C star H as a Hilbert C star H module. And so the adjointable operators on that are just the multiplier algebra of C star H. So this C star G maps to the adjointable operators on C star X, which is the same as multipliers of C star H. And this is non-degenerate. So following Voronovich, I just call this a morphism of C star algebras. For many purposes, you don't want to go to multipliers. You want to go to C star H itself. And an actor is proper if this happens. So proper actor, this means...
Sorry, Ralph, I have a very stupid question.
Yes?
If I may. I understand when H is a groupoid and then C star of H is a C star algebra. But in a bigger generality, when you take just X, which is acted upon by a groupoid, is it a C star algebra in some sense or just a module?
C star X is a Hilbert module over C star H, and then there's a left action.
Okay, good.
And they need the right action to be free and proper for this to work. And also this assumption on the anchor map is needed. Otherwise, I would need some kind of measure family to define my L2 concept on the C star X. But assuming this assumption that I have about this source map being a local homeomorphism and so on, it's all straightforward. And it gives a Hilbert module.
Yeah, thanks.
So there is also the anchor map for this action on H. And since the actions commute, this descends to the orbit space for the right action, which is just H0. And this map should be a proper map. So if this happens, I call the actor proper, and then C star G maps to C star of H. Okay, so another point I should mention is that these actors and proper actors form a category. Well, there's two categories now. The way that composition works is kind of like this. If you have an actor, I suppose G goes to H, H goes to K, then you can define something like H times K. And you can define something like G times H. And you want this to be associative. So these products are not always defined. You need source and range of G, H, and K to match appropriately. But so the rule for the composite actor is that, so this here is again an arrow in K, and this here is an arrow in H. And so this formula here on the right would be an action of G on the arrow space of K. And there's a unique action that makes this formula true. And this is how you compose actors. And going to C star algebras is a functor. So then C star G maps to C star of H, maps to C star of K. And the composition is functorial as you expected. So we have now turned the groupoid C star algebra for étale groupoids into a functor from this groupoid actor category to the category of C star algebras and non-degenerate star homomorphisms. Okay. So if you can somehow produce actors between the boundary path groupoids of graphs, you also get star homomorphisms on the C star algebras. And at some point, Piotr gave a talk where he explained his idea of defining various graph morphisms using maps between the graphs and relations between paths in the graphs. I found the definition very technical. So my way to relate to it was try to understand whether I can do it in a different way. In particular, I was wondering whether these star homomorphisms on the C star algebras come from groupoid actors, and the formulas looked like they should. And so when I went to Florianopolis last year, well, I thought I should probably talk to Gilles about this and try to figure out whether they really come from groupoid actors and how these actors come about, because I also had an idea how one could actually understand these actors in terms of the graphs. So the next important point would then be, can we understand actors I just say graph groupoid now. So this is the boundary path groupoid of a graph, the one that we want to look at for understanding graph algebras. And indeed we can. And well, at first I didn't know what would come out of it, but after you see what comes out, it's kind of obvious how it should go. So that's the main theorem in my paper with Gilles. So the groupoid actors are proper ones. I only care about proper ones at the moment. Proper groupoid actors
I think you might wish to read Groupoid is.
What do I want to do?
Say what the graph Groupoid is.
At the moment, it's a black box for me.
Okay.
So it's the groupoid whose C-star algebra is a graph C-star algebra.
Sure.
And I will characterize it by a simple universal property, which we can understand without knowing what the graph groupoid is.
Okay.
And that's maybe one of the good points about this result. The graph groupoid looks complicated, but actually this is not so bad. So for me, a graph means that you have edges and vertices, and there's the range and source maps, or, well, so an edge goes from its source to its range vertex. And there's another groupoid H, and these proper groupoid actors are equivalent to what I call now non-degenerate Kunz-Krieger. Maybe I should call the whole graph gamma. So the graph gamma is this piece of structure. So Kunz-Krieger gamma families in H. I forgot the word dynamical. So we call these dynamical Kunz-Krieger families because they are analogous to Kunz-Krieger families, but now on the groupoid level, which is a bit like dynamical systems for me. And I should now define what these are. So this is just giving a name to them now writing down. So, and the definition is just take the usual definition of a Kunz-Krieger family in a C-star algebra and replace, well, partial isometries by compact open bisections. So you want to have open.
It was in your abstract, if I remember correctly, right? It was in the abstract.
Yes, could be. There is omega v's in H0, which are compact open subsets. And these are for vertices. And then there is supposed to be compact open bisections. For edges. And bisection, this just means that the source map on this thing and the range map on this thing are injective. And since these maps are local homeomorphisms and these sets are open by assumption, it will be a homeomorphism from TE onto an open subset. So this is my data, and they have the following properties. So the first thing, these omega v's play the role of the projection generators for the Kunz-Krieger algebra, graph algebra, and their intersection corresponds to the product of these projections or orthogonality. So these should be empty for all vertices. Next, my convention is, well, one of the two possibilities. Those who are familiar with this will recognize which one I'm using. So I'm requiring that the source of my bisection, so the source image, which is an open subset of H0, this is supposed to be omega of SE. So this source of the bisection corresponds to the source projection of a partial isometry. So that corresponds just to one of the usual Kunz-Krieger relations. And I want that the range projection is contained in omega of the range of E. And this is now for all edges. then all these ranges should be orthogonal. When these are different. And then there is also the interesting relation about the range projections summing up to the vertex projection. And I ask this for all regular vertices. This means that this disjoint union isn't empty and it's finite.
Sorry, in point 3, you wanted to say that it intersection is empty?
Yes.
Right? Oh, yes. Thank you.
Thanks. And then finally, this is what I call non-degenerate. This is that the disjoint union of these omega v's is all of H0. So when there's a certain, desire to also construct degenerate star homomorphisms between the graph C-star algebras. So some interesting ones fail to be non-degenerate. And I mentioned that the proper actors, they give you only non-degenerate star homomorphisms kind of by design. So if you only take these proper actors, then you can never expect to get degenerate star homomorphisms out. But there's a simple way of generalizing actors by just restricting the object space in your target groupoid. So instead of acting on all of H, you might just act on a subgroupoid of H, where you restrict to a certain subset of the object space. And that's what's happening here. So here this H0 means that I'm kind of having an actor into the restriction of H. Oops, this was not the right notation. So when you have one of these Kunst-Krieger families, which is degenerate, so the union of the omega v's isn't everything, then you can just look at the subgroupoid here, and you get an actor to this subgroupoid. Also, we know that the C-star algebra of such a restriction is a hereditary subalgebra. In C-star of H. So this is what you would expect from a degenerate star homomorphism. The range of this is some hereditary subalgebra, and then it is actually non-degenerate into that one. Okay, so if you look at this definition of a dynamical Kunst-Krieger family, you see that if you now take PV to be the characteristic function of omega V, and the SEs to be the characteristic function of my TE, then this is a Kunst-Krieger family. Kunst-Krieger gamma family in the C-star algebra of H. So the relation that I impose for my dynamical Kunst-Krieger family translate into the conditions that I would ask for a usual Kunst-Krieger gamma family in the C-star algebraic sets. And so you can see how one of these dynamical Kunst-Krieger families generates a star homomorphism. You just, on the graph C-star algebra, you just send the usual graph C-star algebra generators to these characteristic functions here. Okay. So you could have come up with this definition of a dynamical Kunst-Krieger family without knowing anything about groupoid actors. The only thing you need to know is that if you have a bisection So if T in H is a bisection, then well, one of T is a partial isometry. And moreover, you know some things like, so if you multiply these things, you take the convolution of one T and one S. For two bisections, you get the characteristic function of the product of these two bisections, which is just take all pointwise products. And this is again a subset, which is a bisection in the groupoid. And I should have set here compact open. Otherwise, this function here, characteristic function, is not continuous and so on. So this works for compact open bisections. And also, if you take the adjoint of this, you get the characteristic function of the kind of inverse of this bisection. And the source of a bisection happens to be really T star T. And the range of a bisection is T T star if you multiply bisections as subsets in the groupoid. So that's why in my definition, the conditions I impose about the sources and ranges of these bisections tell me something about the source and range projections of these characteristic functions. Okay. I've now described these groupoid actors in a very nice and concrete way. And you can also work out explicitly what kinds of star homomorphisms they induce on the graph C-star algebra. And then you can compare this to the star homomorphisms you get from relation morphisms that were defined by De Castro, D'Andrea, and Hayats. And if you do that, you see that all relation morphisms, as they defined it, come from these dynamical Kunst-Krieger families. So that's the second theorem. Well, relation morphisms are defined if you have two graphs. Gamma and maybe lambda. Well, maybe let's say give is probably a better word here. Give I should have said here degenerate and proper groupoid actors from between these graph groupoids. And even more, we can characterize which degenerate proper groupoid actors arise like this. And of course, you could rephrase this differently, namely give dynamical Kunst-Krieger families. In G lambda. So this is how this theorem is proven. You just write down, given a relation morphism, you write down suitable omega v's and TEs, and notice that the extra conditions that you impose on these relation morphisms are probably admissible or something. There are some adjectives that are needed to make all this work. And if you impose all these adjectives, then you can check that this is indeed one of these dynamical Kunst-Krieger families as defined above. And you notice that they have some extra properties. For instance, here in this construction, the omega v's are just any compact open subsets. When you come from a relation morphism, then these subsets actually are just units of vertices. That's kind of built into the construction of these relation morphisms. So we can only get dynamical Kunst-Krieger families where the omega v's are just unions of cylinder sets defined by vertices, which limits the generality, of course.
Sorry, I have a question. So maybe I missed it. What do you mean by a degenerate actor?
Degenerate actor means an actor into this subgroupoid. So degenerate actor means that you are given, I think, an open subset is probably what I want, or compact open if it's supposed to be proper. So there's a subset Y, and you have an actor into this restriction of Y to this subset.
Okay, thank you.
And this degeneracy corresponds to allowing degenerate star homomorphisms to occur. Yeah. So I should also say that this second part, comparing these dynamical Kunst-Krieger families to relation morphisms, was done by Gilles de Castro because he knows this theory, of course. So I left this to him. And so since I heard from Piotr that Gilles is also speaking in this series very soon, maybe it's best if I don't say much about this, much more than this, because I don't have infinite time and I don't have the biggest expertise in this part of the paper. Maybe I spend my time better if I say more about the groupoid actors, and probably I should now at some point talk about these groupoids, the graph groupoids, and what they have to do with these dynamical Kunst-Krieger families. So where did this universal property here come from? So what you see here, this theorem is really a universal property. You want to say something, Piotr? You look like you want to say something. But I can't hear you.
Okay, so this microphone this is not working. Okay, so I just wanted to confirm that Gilles gives a talk in 2 weeks exactly. So it's a good idea of what you just said. Yeah.
Very good. So this theorem here could be taken as a definition of the graph groupoid if you don't know what it is, because well, in this category of groupoid actors, you can check that isomorphisms are just groupoid isomorphisms. So that's the only way how an actor can be invertible, if it's a groupoid isomorphism. And this universal property here, well, by the Yoneda lemma, basic category theory, determines the graph groupoid uniquely because it tells us exactly what the proper groupoid actors to any other groupoid, any other étale groupoid are. So here would be a possible definition of the graph groupoid. And it's an attractive one because the definition is just a kind of groupoid lifting of the usual definition of the graph C-star algebra. You just replaced Kunst-Krieger families in C-star algebras by dynamical Kunst-Krieger families in groupoids, maybe non-degenerate ones. There is also a category of degenerate proper actors, by the way, but this is less standard, hasn't been studied before, so I don't talk much about it yet. So you might say this is a good definition of the graph groupoid. If you didn't know that graph C-star algebras have groupoid models, but you somehow wanted to lift the construction of a graph C-star algebra to the groupoid level, maybe you would come up with this definition and say, this would be the right universal property that should define the graph groupoid. Well, of course, you want to know now that the graph groupoid that we know from previous work by the C-star algebraists, who just wanted to find some groupoid that realizes the graph C-star algebra, that it should, well, that's the groupoid you get by this definition. So why is that? And this actually goes back to understanding the construction of graph C-star algebras and then also the underlying groupoids in a more general fashion using this groupoid correspondence setup. So if you have a groupoid correspondence, so I now talk about a bit more general situation. So at the moment, G is an étale groupoid. And X is a groupoid correspondence from G to G. Then you can construct C star X, as I mentioned this before. So this is now a C star correspondence on C star G. And maybe let's assume the groupoid correspondence to be proper to simplify the discussion. You don't need this, but the generalization causes some more notation to be required. So let's talk about the simplest case. So C star X is a C star correspondence. And this has a Kunz-Pimsner algebra. This is now also proper, meaning that the left action of C star G is by compact operators on C star X. So I can impose this Kunz-Pimsner covariance condition on all of C star G, and then I can make the Kunz-Pimsner algebra of this C star algebra. And this Kunz-Pimsner algebra has a nice universal property in terms of C star correspondences. And I need another page for writing this down, I guess. So I now want to give you a different version of the universal property of the Kunz-Pimsner algebra. And that goes as follows. So a non-degenerate star homomorphism from the Kunz-Pimsner algebra of any C star correspondence, for instance, the one I just introduced, to another C star algebra D. And I probably should say is equivalent to not given by. That's a bit more precise. So of course you have a star homomorphism on C star of G, but I changed what you normally would do on the Hilbert module part of this C star correspondence. Namely, I want to assume a unitary operator between C star X So it's a unitary operator between this tensor product C star correspondence and D. So I'm using here that C star X is a Hilbert model over C star G, and that C star G maps to D to form this tensor product. This is now a Hilbert D module, so is this. And I want these to be isomorphic in such a way that also the left action of C star G is preserved. So it's really a correspondence isomorphism. This is also a correspondence. This tensor here is the composition of correspondences, by the way. Okay, so the crucial thing here is this kind of composition of C-star correspondences. And this also has a groupoid analog. So if you have groupoid correspondences X and Y with groupoids G, H and K or something. So X is a groupoid correspondence with G and H acting on left and right, and Y has H and K acting. Then you can compose them.
Sorry, I have a question. So is this homomorphism from C star G to D, it doesn't have to be non-degenerate?
I assume it non-degenerate, yes, that's a good point. Non-degenerate is assumed, maybe. And yes, because I want the star homomorphism to be non-degenerate. And it wouldn't work with degenerate star homomorphisms because then the range is strange. And so it only works with non-degenerate maps, the way I've corrected it now. So what is a groupoid analog of composition of C-star correspondences? So this X circle Y means the following. First, you can make a fiber product over H0 because there's actions of H on both, so there's anchor maps to H0 on both spaces. And then you can divide out the relation that XHY is equivalent to XHY like this for all XHY where this makes sense. So it takes the orbit space for the canonical diagonal H action on this space. And this is, again, a groupoid correspondence between G and K as you would expect. So this gives you a reasonable composition of groupoid correspondences. And this really is a groupoid analog of the C-star tensor product, because if you are taking C star X tensor over C star H with C star Y, that's the same as C star X circle Y. So you can lift the tensor product of C star correspondence to the groupoid level. And now you can do something like this Kunz-Pimsner algebra universal property in the groupoid correspondence framework. So you might wonder whether there is a groupoid having a similar property. Well, what should D now be? And to make things simple, you just take D, replace it by a space. So you want to have the topological space on which the groupoid G is acting. This composition here doesn't require more than an H action on Y. You don't need any K to act on Y on the right. It doesn't play a role in this construction. So you can still do that if Y is just a G, just an H space. And so this is the definition of the groupoid model of a groupoid correspondence. This is a groupoid. So a groupoid correspondence as above, X goes from G to G. This is now a groupoid, maybe M for model, groupoid model. And I wanted to describe it using actions on spaces. And actions on spaces are naturally equivalent two things. So there is a G action on the space Y, and there is let's take a proper groupoid correspondence to simplify the setup. So you want a G equivariant homeomorphism from this X circle Y to Y. This is how the groupoid correspondence X is acting on Y. And I restrict attention to proper groupoid correspondence because my time is already running out. If you want to do, I have 20 minutes left, I think, and there's many things I want to talk about still. No, wait a moment. I have half an hour, right?
Yeah, you have 33 minutes and some
Yes,
seconds.
so I was confused. I was thinking of starting at 17, so I still have quite a bit of time. Very good. So I might actually well, I can say a few words about the generalization then. So for proper correspondences, this theory is a bit older. It was done by Albandic already around 2015, so it's now around 10 years old in his dissertation. More recently, based on the dissertation of another student, Celso Antunes, whom I mentioned before, the different paper we wrote together, he did something for a single correspondence in the kind of relative Kunz-Pimsner algebra situation. So if we go back to the universal property of the Kunz-Pimsner algebra, this works for the absolute Kunz-Pimsner algebra, where you assume that the left action is bicompact on the whole C-star algebra, and you impose this Kunz-Pimsner covariance condition on the whole C-star algebra. Now, if you want to treat non-proper correspondences, C-star correspondences, then you need to, well, you can only impose the Kunz-Pimsner covariance condition on some ideal. There's a standard choice, but it's not so important. There's also relative construction where you just pick the ideal as you like. It's a free variable. And so there is a version of that also on the groupoid level, where you specify something like an ideal. Well, what could correspond to an ideal? The way to get ideals in groupoid C-star algebras is to take open invariant subsets. So for relatively proper groupoid correspondence, now you have the groupoid G, you have the correspondence X, and you have a subset R. In the object space of G, which is open and G invariant. So this would correspond to the ideal in the coefficient algebra you use to make a relative Kunz-Pimsner algebra. And then there is the condition so properness would mean that the canonical map from X mod G, should we write Rx here, so this is contained in X mod G. The map from X mod G to all of G0 would be assumed to be proper if you want to define a proper groupoid correspondence. Now here I restrict to this preimage of R and only ask the restriction here to be a proper map on top. That's a weaker condition. For instance, R could be empty. In that case, this is also an empty set and the condition is empty. So every groupoid correspondence becomes relatively proper on the empty set. One of these stupid statements about empty sets which are trivial. And so there is also a notion of groupoid model for relatively proper groupoid correspondences. So there you would ask, instead of, so in the relatively proper case, so you don't ask this map from X circle Y to Y to be a homeomorphism onto all of Y. You only want it to be a homeomorphism onto an open subset, which is big enough to contain the preimage of R. Here I'm using the anchor map for the action. It goes from Y to G0. So I can take this preimage of R. Okay, and so this universal property, as it turns out, there's one more technical condition I don't write down. There's a recent paper by me about groupoid models for relative Kunz-Pimsner algebras, where you can find the details of this construction. So I should now probably give you the main properties of this construction. So the theorem says that if you, first of all, there exists such a groupoid model for this situation. And if you take its C-star algebra, you get the relative Kunz-Pimsner algebra for the correspondent C-star X relative to the ideal of C-star G restricted to R. This is supposed to be an R. It looks a bit strange. Maybe I should draw this R again. Okay.
So could you elaborate a little bit on this theory of relativity? You are doing it relative to an ideal, right?
Yes. So on the C-star level, this ideal is where you ask for this Kunz-Pimsner covariance condition. So this thing maps into the compacts on C-star X. And the compacts on C-star X sit, of course, in the Toeplitz algebra of C-star X. And this also maps into C-star G as an ideal. This also sits in there. This diagram doesn't commute, but when you pass to the quotient by, in the relative Kunz-Pimsner algebra, you make this diagram commute by dividing out the relation you get from this. So there's two maps here, phi 1 and phi 2. And you divide out
By the difference, yeah.
Yes.
Mm-hmm.
And this is how you make Kunst-Pimsner algebras, always a relation like this. And here you just choose the ideal that is given to you because you are given the subset R.
Mm-hmm.
The reason why I like the relative version of this is that Katsura's ideal is not always known to be of this form. So there's a kind of standard choice if you have a C-star correspondence and want to make some Kunst-Pimsner algebra out of it. Katsura defined a certain ideal. However, the way he defined it, if you have groupoid C-star algebras, there are things like non-exact groupoids. So there are certain reasons why difficult analysis might prevent you from describing this ideal in groupoid terms. So I just be happy with a relative version where you give me the subset R and then you have an ideal out of that. And maybe to make all this less abstract, we probably should think about an example instead of doing more theory. So what would be the simplest kind of example that's interesting of a graph? Maybe you like the Kunst algebra O2. So let's look at the example of the 2 rows graph, 1 vertex, 2 edges. So what happens in this situation? Of course, the groupoid G is just the 1-point groupoid. I write PT for point. It has 1 object, 1 arrow, discrete topology, nothing interesting, you might say. The smallest groupoid that's not empty. And X has 2 points. Maybe I draw it like this. Yeah, okay. So 2 points. Since my groupoid G is so simple, the actions of G on X are unique. Any space carries unique action of this 1-point groupoid. I give it X this action, and this makes it into a correspondence. It's also proper because everything is finite, so no reason for complicated things. And what is an action of G, of this correspondence? And R, I want the Kunst algebra, not the Kunst-Teplitz algebra, so I take R to be all of G0, which is also just the 1 point. I could take the empty one instead. If I did that, I would produce the Kunst-Teplitz algebra, but it gets a bit more difficult because I need then an extra condition, which I didn't talk about before because it's technical. So let's do this version, which is more interesting anyway, because we all like Kunst algebras much more than Kunst-Teplitz algebras, I guess. So what is an action? What's an action on Y? So the G action is nothing. It's unique. So in that sense, it's no data. It's always there, no condition, no extra data. So the only interesting thing is the map from this X circle Y to Y. Now, X circle Y in this case is just X product Y, which, if you like, is a disjoint union of 2 copies of Y. But I won't use this in the following, at least not immediately.
Sorry, do we know anything about Y, or is it just an arbitrary
Y is
thing?
just a space. So the point is, I want to understand the universal property, and I want to argue why the well-known groupoid that you get for the Kunst algebra has this universal property.
Say it again, Y is what?
Y is any space.
Any space.
That's
okay.
important because
Okay.
I want to do a universal property.
Okay.
So I
Yeah,
want to
yeah.
describe actions of this in any space, and then you will realize that the groupoid whose actions are described in a moment is exactly the usual Kunst algebra groupoid.
Mm-hmm.
Okay, so this X circle Y that occurred in my definition of an action is just the product X times Y. And since I'm in the absolute case, I have a homeomorphism from Y to X circle Y. Okay, now if I have this map, I can actually iterate it. So if I have X circle Y, well, I can first eat 1 X into Y, So doing something like identity circle, maybe I call this here theta, maybe. And then I do another theta. And so I can also absorb two x's into y, and this is also a homeomorphism because I have two homeomorphism. And so I get, and then now notice that this circle is just taking usual products. So I get homeomorphisms from xn times y to y for all n in n. And now I could just forget the y factor and project to xn. Okay, so what you're doing is you're looking at this homeomorphism on x circle n, and you can see that you have here kind of 2 to the n elements in xn. You take a point in y, take a pre-image, and you record the letters that you see in x to the n, so which component the pre-image belongs to, and you forget the y part here. Okay, now the way these maps are constructed iteratively, you notice that the following happens. So you have these maps for all n, and there is also a canonical projection from xn plus 1 to xn, which forgets the last letter. In a word, and this diagram commutes. So by the way it's constructed, so if you have this map on x circle n and do it one more time, you only change the last letter but not the first n letters, because you are, well, that's how it's defined. So, so you get a continuous map from y to this, well, now the product over all natural numbers. So the infinite product, count to be infinite product of x, and remember this is just, so we have two elements, maybe one, so 0, 1 to the power n. So it's just infinite words in two letters. The 2 comes because they had the 2 rows. If I had taken a row with 5 petals, I would have gotten 5 letters here. And this is, well, if you have seen the Groupoid of the Kunstalgebra, you know that this is its object space. So this is the anchor map of the action of this Groupoid, of the boundary path Groupoid of this graph. And what else is there to be said? We also had this map from x circle y to y. So there is a bit more, because now I identify x times y. This actually is 2 copies of y. And I have a map from this onto y, which was my theta. And so this gives me now 2 partial homeomorphisms. And these are homeomorphisms onto complementary compact open subsets. And if you look at how this map interacts with my maps to the xn's, you see that these correspond to the shift map. So maybe I should have called them sigma 0 and sigma theta 0, theta 2, 1 and 0 and 1, because then the next thing gets a bit nicer. So I number 0, 1 here with the shift maps. You can send an infinite word to the word 0 omega and 1 omega, append a letter in front. These are homeomorphisms from the space to complementary compact open subsets. And you can work out that this canonical map from Y to this infinite product space just intertwines the theta maps and these maps here. And now these local homeomorphisms on this space generate the Kunz groupoid. So the groupoid model of the Kunz algebra. Generate maybe as a German groupoid or something. So you should take products of these shifts and their partial inverses, partially defined inverses, and then you make a Renaud-Diacono groupoid out of this stuff. And this is how the groupoid for the Kunz algebra actually was defined. And since the action of my x on y is specified by this map here, by this map theta, you can realize that indeed an action of this groupoid for the Kunz algebra is exactly the actions I defined upstairs. So I think this is all I want to say about this example, since my time is now really running out. I have roughly 10 minutes, I think. And I wanted to say something more about isomorphisms.
12 minutes.
Yeah, 12 minutes, exactly. So, so where are we now? I have given you an idea why these universal properties might have something to do with the groupoid models of graph algebras. So I did it only for O2 to make it more concrete. And if I had done it for a general graph, it would have been quite similar. So you could also do this analysis by hand for graph groupoids for general graphs. So I think I don't want to say more about the proofs of my theorems now. So we now just believe that we have understood why the groupoid model, the boundary path groupoid of a graph has this interesting universal property. Now, I mentioned that actors are a category. And a nice feature about categories is we can compose morphisms. So there's 4 categories. You can take actors, proper actors, non-degenerate. Degenerate was I didn't define. So the degenerate actors are more general than actors. Actors are by definition assumed non-degenerate for historical reasons. I don't want to change my notation again. So there's 4 categories where you allow degenerate actors or proper degenerate actors, and they all form, well, categories. And therefore, you also get a composition of these graph morphisms, or so if you have 2 graphs again, so the graph gamma and you have lambda, and if you have an actor between those, and then you have another actor to another groupoid, could be another graph groupoid, doesn't have to be, then you can compose them and get an actor from here to there. So this gives you a composition for these dynamical Kunst-Krieger families. And it turns out that this generalizes the composition that exists on relation morphisms. So for these relation morphisms that were defined combinatorially by Gilles de Castro and Francisco Andrea and Piotr Hayats, there is also a composition, and I think it's pretty mysterious why this works, but it does. At least for me, it's mysterious. Maybe they understand it. This here is much clearer, I think. So with groupoid actors, there are categories, so you can, of course, compose things. And it's an exercise to work out how this would look like on concrete things, so that you can compose dynamical Kunst-Krieger families. Another thing which is a bit more interesting is, how about isomorphisms? So what if an actor, proper actor automatically, an isomorphism of C-star algebras? So imagine that you have 2 groupoids and you have an actor from G to H. And this induces a morphism into multipliers, and we assume that it goes into C star H, so it's proper. And this is an isomorphism of C star algebras. You might wonder, does it follow that the actor was a groupoid isomorphism? This is interesting also in connection with these relation morphisms, because it might well be that some combinatorial construction of a relation morphism gives you a star morphism of graph C star algebras, which is invertible, but the inverse maybe is not, at least not obviously, coming from a relation morphism. So you might wonder, does it come from some dynamical Kunst-Krieger family? And in the paper with Gilles, there is also an example of this. So it's pretty easy to make examples where you're, well, where the C star is just matrix algebras. So
Ralph, allow me to make a quick comment, because you touched upon a subject which is very dear to my heart. You don't have to go as far as relations. I mean, if you study the moves that people so much like and enjoy, that give you isomorphisms between graph C-star algebras of different graphs, many of them, you know, outsplit, shift, you name it, they can be obtained just as functorially from our graph homomorphism or path homomorphisms of graphs. However, very much like you pointed in here, when you look at the inverses, I mean, they are isomorphisms after all.
Yes.
Then we found out that we have to enlarge our categories. So we have a paper with Gilles and a bunch of other people where we have extended functoriality of path homomorphism of graphs, and this is exactly designed to accommodate the inverses. roughly speaking, the thing is that you have to also use the adjoints. So you cannot just go between paths as we do in the relations. You have to somehow use also paths in the extended graphs, but it's a longer story. I don't want to go into it. However, if I can still steal a little bit of your time, if I understood you correctly, you mentioned at a certain point that is a bit mysterious of why we have composability, right? I mean, why is it a category? And I completely agree with you. This is very mysterious, and this was a very tough cookie to crack. But now I have a certain idea of how we can explain it. So if you just look at the first Kunz-Krieger relation, well, basically when we're working on these extended path homomorphisms of graphs, you go to graph inverse semigroups. And you just take homomorphism of graph inverse semigroups, and they give you a homomorphism of conpath algebras, or if you are sister algebraic, Teplitz graph sister algebras. Okay, and then, and this is a beautiful idea of Gilles proved that the regularity condition, which is a very complicated technical condition, is actually equivalent. Is actually equivalent to the preservation of the ideal generated by the second Kunz-Krieger relation, and then it's obvious that you can compose it.
Okay, very
because
good.
If you preserve ideals, then you preserve ideals. That's composable condition. And it's equivalent to the regularity condition. But this is a very roundabout explanation. So I completely agree with you that it's kind of mysterious.
Yes. Another possible proof of this would be to use the composition of groupoid actors and work out that the extra conditions you need for the groupoid actor to come from a relation morphism is preserved under this composition. This might be a kind of very short computation, I hope, but I haven't done it myself. I would think this might be a topic for Gilles to do if he wants to go this direction. Because he might also like your proof better, which is more combinatorial. So in our paper with Gilles de Castro, there's an example. So these are very, very small graphs. You see there are no infinite paths, only finite paths. And if you look at the boundary path groupoids, you see that they have both just 3 points, and they're all equivalent. So the boundary path groupoid is also just the pair groupoid. So G1 and G2 are both just pair groupoids on a 3-element set x times x, where x has 3 points. So very simple example. And you can directly see that the graph groupoids here are isomorphic. So there must be isomorphisms, therefore groupoid actors, and in the paper we write down the dynamical Kunz-Krieger families for this. Since I have almost no time left, I think I won't copy the formulas from the paper. You can, of course, try to guess them all. It's a nice exercise maybe to figure out what possible groupoid actors there exist between them and to translate them into dynamical Kunz-Krieger families. And in this example, one of them is clearly coming from a relation morphism and one, the inverse, isn't. So you get very simple examples for this phenomenon. With graph algebras, the most interesting ones are the simple ones. And when the graph algebra is simple, then we know that we can go backwards from a groupoid isomorphism to from a C-star isomorphism to a groupoid isomorphism. The reason being that if you start with an actor and make a star homomorphism out of it, then you always preserve functions on the units. So this always maps C0 of G0 to C0 of H0. And if you are lucky, then functions on the units are a Cartan subalgebra in the groupoid C-star algebra, and then you can use Renaud's theory of Cartan inclusions to argue that the groupoid is naturally attached to this inclusion of a Cartan subalgebra. And so this allows you then to lift the C-star algebra isomorphism to a groupoid isomorphism. Okay, that's in my paper with Gilles. But Gilles mentioned to me that at least for graph groupoids, this should be true in general without any Cartan subalgebra restriction. When I was back from Brazil, my former student Jonathan Taylor visited me, and we were chatting about current research, and I mentioned to him this question, whether it might be true that if you have an actor, then such that the induced morphism of C albers is invertible, then the actor must be invertible, and it seemed plausible to both of us, and we tried to prove it. While he was here, we could do the more algebraic version. So when you have something like level path algebras, where you have better algebraic features, and we could make this proof. And we had hoped that we might also do it with C-star algebras. And well, the paper isn't out yet, unfortunately. So I think the current status is that, first of all, Sven Raum joined us because he also had some good ideas. So this is now a project by me and Sven Raum and Jonathan Taylor. And so the goal would be if an actor G to H induces an isomorphism from C star G to C star H, it is an isomorphism of Groupoid. So the relevance would be that if we know this, then whenever we get an isomorphism of Groupoid C star albers from an actor, then, well, the inverse also comes from a Groupoid actor, because you have an isomorphism of Groupoids. So for instance, the inverse of a graph algebra isomorphism coming from some dynamical Kunst-Krieger family is also given by a dynamical Kunst-Krieger family. So the current status is that we know this if we use reduced C-star algebras and have Hausdorff groupoids. And I think the proof in that case looks solid to me, although, well, it's not even yet a preprint. So, but let's say it's proven for reduced C-star algebras. And Hausdorff groupoids. And the proof turned out to be more subtle than you might think. So it looks like a very easy question, but we have to resort to some interesting theories. I have no time to talk about obviously because I should finish now. So the generalization to non-Hausdorff groupoids and full C-star algebras is, let's say, work in progress. And I think I should now stop here.
Thank you so much for a very fascinating talk. Thank you. Okay. Any further questions? There are many clapping hands floating around, which is really cool. Thank you, guys. Tomek, fire at will. But unmute yourself.
I have two questions. So first question, let me say first, the property of functors. Functors admit natural transformations.
Indeed.
My question is there an analog for actors inducing transformations of correspondences, sister correspondences?
Yes. Bisections, global bisections, we can conjugate by those.
Global bisection conjugate. Okay,
so if you have a global bisection, this is like an isometry, so you can, or even a unitary. Well, there might be things, if you work with degenerate actors, you might even work with partial isometries and things, but let's take global bisections. So they would correspond to unitaries in the C-star algebra, and they define inner automorphisms. So the simplest case would be groups where you have. So I didn't say this, but if you have groups, then actors that are group homomorphisms, and natural transformations are given by elements, and inner automorphisms coming from elements. But if you want to do this, then I would recommend to work right away in the Groupoid correspondence by category. So there you have even a bicategory, so it's kind of more structure. The disadvantage is that you only get C-star correspondence, not C-star homomorphisms. So for this current project, we wanted to get star homomorphisms of C-star algebras, not some generalized morphisms. So that's why we took actors.
Okay, thank you. So my second question is about extending this, at least formally, this theory beyond étale groupoids. For instance, in the case of topological graphs.
Good question.
Topological graphs give étale groupoids. And they're also groupoid models.
Okay.
Yes.
They are still group. Okay.
Yes. So if you have any groupoid correspondence, you always get an étale groupoid as a groupoid model.
Okay.
So, and doing non-étale groupoids to start with, this might be like topological quivers. And I have some misgivings about this theory being possible. One problem is that many of my results are in the proper case only, and these topological quivers are kind of never proper, things like that. Of course, you could take the empty. So there's a chance it might work, but I never had reason to consider this seriously. So far, this theory has kept me occupied well enough. I would be a bit skeptical whether it will work, but I might be overly pessimistic. So I don't know.
Is there any chance that C-star algebras of graphs can be somehow characterized in terms of groupoid models?
What do you mean? I mean, there's a C-star algebra, also groupoid
but
model.
Abstractly, not in terms of Kunst-Krüger families, but by some properties.
Yes, there are a limit in the bicategory of C-star correspondences. So, or co-limit depending on your conventions. So if I'm looking at the groupoid C-star algebra and the C-star correspondence, this is an endomorphism in the C-star correspondence bicategory. And depending on conventions, whether arrows go from right to left or left to right, I should take the limit or co-limit. And if my C-star correspondence is proper, then the limit will be the absolute Kunst-Pimsner algebra.
Okay. May I ask another question?
Yes.
It's not maybe related to graphs, but there's some formal similarity between theory of groupoids and its infinitesimal counterparts, Lie algebroids.
Indeed.
And in the realm of Lie algebroids, we have two kinds of morphisms between them. There are morphisms and comorphisms.
Yeah, and
so
I think that
actors.
some of my co-authors mentioned that these comorphisms are like these actors.
Okay. But at least formally they correspond to.
I never checked this myself, and so you should. And of course, there's some translation going on because I work on the groupoid level, and so you have to first go to groupoids and then differentiate to Lie algebroids. And I think if you do this, you should get these comorphisms out. But don't trust me on this. I never did this myself. I sometimes work with Lie algebroids, but usually with co-authors who know such things, and I don't have to bother about them.
Okay, thank you.
Okay. Anybody else? Mark? No. Adam?
I'm happy, thank you.
Jean? Dimitris? Okay. Nobody wants to volunteer. Okay. Marius, you saved the day.
So I have two questions. So first is connected to what you just told us about topological graphs. So do you know what's the groupoid model for topological graphs, or where I could find this?
So for topological graphs, first of all, I remember that Yiend has a groupoid model for topological higher rank graphs. And I think that rank 1 topological graphs should have been done before, but I don't remember who did it. It might also be in one of Katsura's many papers about this, but maybe. So Katsura doesn't really use groupoid techniques so often. He has other techniques usually.
Yeah, I also think that.
So I would look for Yin's papers first and check his references if there's anything for topological graphs as well, specialized for them.
Okay, thank you. And the second question is probably at the very beginning, you said that actors usually give you maps into multiplier algebras.
Yes.
Right. And do you have any idea, or did you think about what would the conditions be on the dynamical conscrigger you had for graphs to get maps into multipliers, not only into...
It's very easy, actually. I didn't want to spend time on it. So in my definition here, I said compact open. And if you want to have non-proper, you just take here kind of closed and open.
Oh, I see.
So clopen. If they're no longer compact, then this makes this kind of a non-proper map. That's because in this anchor map, so omega v is the pre-image of a vertex. So there's an anchor map from H0 onto the G0, which here is just a vertex set. And the map being proper says that these sets are compact. And they're always closed and open because we have discrete topology on the vertex set. And so that's your non-proper actors.
Okay, just this, you change this one condition.
Yes, of course.
That's it. Okay.
Also here, but that follows. I think compactness here might follow because the source of T is omega SE, so this compactness here is anyway comes for free. So in two places you have to replace compact open by clopen.
Okay, thank you.
Anybody else? Anybody else going once? Anybody else going twice? Anybody else sold? Let us danke schön, our speaker again. Thank you so much.
You're welcome, and thanks for the invitation.
Our pleasure. Let me stop recording.